Hi, everyone. My name is Jan Ittner, and I'm here with my colleague Mateusz Soko. We are both with BCG Gamma, which is the data science arm of the Boston Consulting Group. And today we'll give you an overview of FACET, an open source library we created for global model explanations. So let's dive right in. Yeah, so explaining models is central also to our work. Yeah? For many reasons, right? I mean, first, of course, to make sure that models are built the right way and they do what they're supposed to do. Also, using insight from models to support business decisions. Yeah, often it's not enough to predict. We also need to understand why and what, and sort of how to optimize results. Then, of course, explaining our models to the decision makers, who are often not data scientists, but they need to trust in the model and what it does and why. And last but not least, making sure models do not validate ethical principles, yeah, such as bias, for example. And of course, explaining models has been around all the time. Yeah, starting with very simple but tried approaches like just looking at the coefficients of a linear model, looking at feature importance. I mean, it's something anyone almost does by standard after fitting a model. SHAP has been very popular in the past few years to look at explaining individual model predictions. And well, with FACET we add one new tool to that arsenal, looking at how features interact with each other, right? The statistical dependencies between features. How do they complement each other, or how do they duplicate each other? And that's what FACET is about. And we can see that in more detail on the next page. So there's two things that FACET looks at for pairs of features, right? And the explanations that FACET delivers are always for groups of two features. One is to measure how much does any pair of features synergize, which means one feature makes the other stronger. Take an example in a healthcare context that maybe age has to be considered depending on the gender, right? I don't know, for example, for cardiovascular diseases, that we say, okay, that the interpretation of age varies based on whether you're talking about a man or a woman. That also means, for the data scientist, for modeling, removing one feature will not only sort of remove that information from the model, but it may also reduce the impact of other features that are in the model because they are stronger interpreted in context. That's synergy. The other thing we quantify is redundancy between two features. And that is, how do two features actually do the same for the outcome? How do they duplicate information? Yeah, so for example, again, if you take a healthcare example or a health example, body mass index or waist to height ratio are two ways to quantify, let's say, body shape, right, or obesity, and that can play a role in different diagnoses or predictions. These two are different KPIs, but they will be redundant because normally when you have a high BMI, you will also have a higher waist to height ratio, right? So there's redundancy, and that's really important because redundancy brings many problems. Yeah. For example, if you look at the importance of features, if two features in a model do the same, they have to share the credit, and their feature importance will look less just because of the presence of the second feature. And I mean, if you look in the literature, also for SHAP, many problems with SHAP have been pointed out in the past, and a lot of that has to do with redundancy. So understanding that in your model is very important. And you might say, yeah, of course, you can go in and for example, calculate a Pearson correlation, but that only captures part of the redundancy, right? That only captures redundancy when that's in a linear relationship between features. And the approach we're taking here is irrespective of the type of relationship, right? It also works in nonlinear cases. Okay, let's head to the next page. So just very briefly, because FACET, so how does FACET work behind the scenes? There's also a paper that you can find on the GitHub repo, a link to that that explains more detail. But just very briefly, SHAP is an approach that explains individual model predictions, and it does so by giving you a so-called SHAP value for every feature. And the interpretation of that is that it tries to explain for every feature sort of what contribution it makes to the overall prediction. The total contribution of all features is seen as the difference between the mean prediction, your expectation without knowing any information, and the actual prediction for a feature. So if you, for example, for a model expect to get on average, if you average all the possible predictions and you end up at 17, but for this individual data point, you get a prediction of 21, you want to explain why is this 4 points above average? And SHAP would tell you, well, because of feature A being having this certain value in this observation, the prediction would actually have gone down by 1.8 points and so on. But feature D increases the prediction by 3.7 and so on. So basically, all the individual explanations for the features add up to the difference between the mean and the actual prediction. And that means you get a sense of how do the individual features contribute to the overall outcome. Next page, please. Now, what we do is, because we want to take a global perspective, we when you have a data set, basically we take all of the observations, we calculate the SHAP values for all of them, and then we form vectors. So for every feature, you get a vector of all the SHAP values for the different observations, right? For feature A, if you have n observations, you have a vector of magnitude, of size n. PA, then for feature B, you have a vector of the same size. And the idea here, the basic idea is that now if we look at these two vectors and the angle between these two vectors, we can see how much these two features are working in tandem. So first of all, the magnitude of the vector is a measure of feature importance. If the two features are independent, that means that these two vectors are orthogonal, which means basically just knowing the SHAP values of feature A, you can't make any conclusions about what you expect for the SHAP values of B, because they do two different things for the predictions. The more they are parallel, or the smaller the angle between the two, the more you can sort of derive the SHAP values from B for A, which means that B is very closely associated with feature A. Now, there's more to that, and I can't go too deep into the explanations. Basically, you get two vectors. One is the general vector of SHAP values, and then there's also interaction values. But if we go to the next page, and that's really just to give you a sense of what happens. What we do is we take the SHAP vector and the SHAP interaction vector, and we do an orthogonal decomposition of these vectors that allow us to quantify in magnitude the synergistic parts of the relationship of two features and the redundant part of between two features, and also sort of how much of the two features is independent. So how much is feature A using information from feature B to get better? How much is duplicated between these two features, and how much is really truly independent contributions to the prediction of both? If we go to the next page. Yeah, so I mean, Mateusz will go into the details and show a demonstration of this, how it looks in practice, because we think it's much better just to see it with an example. But you'll see these visualizations in a moment. On the left-hand side, you see a matrix that we use both to show either synergy or redundancy, where the same features are on both axes of the matrix. And as an added bonus, the feature importance is expressed as the size of the rows or the columns, so you can immediately see which features are the most important ones. And then the fields show you the degree of synergy or redundancy between pairs of features. The same data, but visualized in a different way, is with the dendrograms that give you a better breakdown of which features actually belong together in clusters. And it's really just a hierarchical clustering based on the using synergy and redundancy as distance measures. Okay, just one preview on the next page. Another thing that we have incorporated in FACET, and that's also something that we often use in sort of as a second step after looking into synergy and redundancy, is simulations. I mean, these are partial dependency plots. but enriched with confidence bands, so we know, okay, how certain can we be about the outcome of the simulation. We usually do these with features for which we have confirmed that they have no redundancies with other features. So we know that we're not constructing infeasible scenarios, and that we are sure that we can sort of freely modify values of these features in the model without having to worry about other statistically dependent features. And we'll see an example of that as well. With that said, I hand over to you, Mateusz, for the demonstration of the library.
Mm-hmm. Sure, thank you. So I will change to the move to the notebook. Mm-hmm. Okay, so in this short demo, we will see an exemplary workflow with FACET, how to perform simulation, how to analyze these components of synergy and redundancy, and to make some statements for a client. So just to introduce, our FACET ecosystem is comprised of FACET library that contains core functionality that we've shown, and also scikit-learn-df, which is basically a library built on top of scikit-learn to improve the software engineering experience that we will also show you in this tutorial. So first, let's introduce our business problem. So let's imagine that we've been approached by a construction company. So it's a problem from civil engineering domain. They would like to improve their products. And one of them is concrete, which is basically a mixture of several ingredients. They utilize domain-specific knowledge, what should be the proportions of the compounds to make this concrete as strong as possible. But they're curious if we can utilize data science techniques to improve it even further based on the data that they collected throughout the years. So for this purpose, we are using a data set from UCI machine learning database. First, we download the data set and load it. Here we see that the target variable that we're interested in is compressive strength. And the features that we're going to use are basically amounts of each components, like amount of cement, water, or superplasticizer. So within this mixture that creates then the concrete. So we load it, then we don't need to do any pre-processing for this presentation. We just adjust feature names to make them more concise, and we can move to building our pipeline. So we will use the sklearn-df. As you can see, the regressors that we're using, random forest regressor and gradient boosting regressor, has this df at the end, which means that for the whole pipeline, we will retain data frame information like columns or indexes. So we won't end up with bare NumPy arrays at any stage. So this is one convenience within this workflow. And another thing that we are interested at the level of pipeline definition is hyperparameter tuning. So here we set up distributions for each of the parameter that we would like to tune. And as you can see, we're using a parameter space object that wraps our pipelines, and we set up SciPy distributions that will be sampled here. So we build up our two pipelines that we would like to utilize. And now we can move to one of the most important classes within FACET, which is a learner selector. Learner selector will perform training, cross-validation, and evaluation of the test set, everything within a single fit. And here you can see that we're passing the parameter spaces that we defined, what kind of search we would like to perform. So here we're using a scikit-learn randomized search, and also we define a cross-validation approach that we're using. We perform a fitting, and after that we can access results via summary report method. And basically here we can see the ranking of all configurations, and we see that the gradient boosting regressor with this specific parameterization acquired the best score of over 93% on R squared score, which we are content with. So we would like to use this specific model. We can access this configuration with a best estimator attribute. And now we can move to actually this inspection part.
One additional comment here. I mean, we also built the learner selector because we wanted to create a simple means for our own use to have multiple types of models compete against each other. So the choice of model here is also a parameter, right? So whether it's random forest or gradient boosting in this case.
So now we move to the second and most important class present in our library. So this one is a learner inspector to which we pass this best estimator. And here within a fit, the SHAP calculation occurs. And now we can start inspecting our ML model. First, what we've got access to are SHAP values. So basically the SHAP values of each feature. And here we can already see what's going to be important for later. We see that superplasticizer is below 0.1, where water is about between 0.1 and 0.15. That's going to be important in the later part. But overall, that's all what you see here. Now we would like to actually inspect these relationships and interactions between features. So first that we're interested in is redundancy. So let's move to redundancy matrix that we build. And first that we spot here is a high redundancy between superplasticizer and water features. Here you can see that they're marked with 37%. Overall, other values aren't really that high. And what was mentioned in a presentation, the width and height of each column and row corresponds to a specific SHAP value. So this is another way of conveying a message how important a feature is. So for example, you can see that fly ash is so thin that no numbers are displayed here. So that's how this additional information is presented here. So moving from redundancy to the synergy part, here we can also spot some synergy. These values are a little bit lower, but still we can see that, for example, superplasticizer and fine aggregation is 16, which is higher than for water. So if we plan to get rid of that excessive redundancy, we need to decide whether to drop superplasticizer of water or water. So that might be to drop a water as it has, for example, a lower value for fine aggregation that we going to retain compared to the superplasticizer. Fly ash and coarse aggregation are the least important. So for example, we might consider dropping both of them. And this is basically the synergy matrix visualization. Another plot that we also seen in the presentation was a dendrogram. So right now we can move to it for a redundancy. It's basically a combination of the previous that we've seen, but represented as a tree here. So within this phase, we might, for example, decide to drop fly ash and coarse aggregation, and, for example, water to get rid of this excessive redundancy that we identified here. So we can see that these two features join pretty early, which corresponds to that redundancy that we've seen before.
Yeah. And we would drop water here, despite, I mean, you could say water is more important, right? It has a slightly higher importance here. But we looked mostly at the synergy with other features, and their superplasticizer had the slight edge. And I mean, the expectation also is that depending on how the model handles two redundant features, it's kind of random which feature gets used more. So in this case, the choice is for water.
So now we rerun the whole pipeline on a reduced data set. So we defined which one are redundant or weak. We say to drop them, and we rerun our pipeline. We again access summary report, and we see that we maintain the high score on R-squared that we've seen before. So here we've got over 92%. And we rerun our learner inspector to see how these visualizations changed. So first, we can move to the SHAP values. And here, Now we see that superplasticizer that before was below 0.1, now it's almost 0.2, so it almost doubled, which we might suppose it happened due to dropping the water feature, that it shared a lot of redundancy. The another visualization that we repeat is redundancy matrix. And here we see that all values are basically close to 0. So we basically got rid of this excessive redundancy. Again, looking at the synergy, on the other hand, we managed to preserve some of it. For example, for fine aggregation, we see with other features that it has the present synergy values, and basically that's something that we paid attention to.
Yeah, maybe one comment here. You can see synergy is not symmetrical. So the feature fine aggregate gets a lot of help from other features. We read this row-wise, we read it across. So fine aggregate gets help from cement, superplasticizer, age, and so on. But other features don't depend on fine aggregate in return. And that's perfectly fair, because sometimes, I mean, it means that other features can stand on their own, but they give help to other features just as well.
Mm-hmm. So this concludes our part where we inspected our model, we built our pipeline, we performed training and testing part. Now we would like to come up with a story for our client to provide some recommendation or a statement how they can actually improve the business problem that we mentioned at the beginning. And for that purpose, we're going to perform some simulations. So just to recap, for a simulation, we select a feature. So first, we're going to select cement, as this was one of the most influential ones. We're going to create partitions. Within each partition, we will set the value to the average within this partition. And then we will run the prediction on this augmented data set. Then we should see some trend that should help us make this statement or a recommendation for our client. So let's run a simulation for cement. And here we basically get this plot that agrees with a domain knowledge that we learned from a client. So the more cement we put into a mixture, the stronger it should get. So it agrees with what we learned. And the recommendation that we might give is that client could increase cement amount to 350, and they should expect an uplift of about 5 points here, compared to the baseline that was present in the data set that they provided. And another important thing here is that we should pay attention to the support below. So here you can see how many samples were present in each partition. And this is important because sometimes there might be some unusual behaviors, for example, at the ends, like a huge jump or a huge drop. And this could be potentially explained if there are only a few samples there. So this is important to interpret plot together with a support below.
Yeah. So the intuition of this chart is, basically looking back in the past, and all the data points we have, we say, what if we had always used cement, for example, an amount of 400.0? How would this have changed the outcomes, the historical outcomes? So compared to the horizontal green line, which is the baseline, I would say if we had consistently kept cement at 400, we could have expected on average an uptick of 12 points here. Yeah. And the same goes, well, for 350, it would have been an uptick of 5. So this also allows us to have trade-off discussions. So there might be a component of cost, for example, for a client, or feasibility, saying, well, it's very hard to achieve 400 on a consistent basis. And all of that could go into discussion saying, well, if we try to control this parameter more and we try to stay, at least we try to stay above 350, then there's already some gain, as one can be seen here in the simulation.
I just wanted to chime in and give you guys about 4.5 minutes.
Maybe just a quick one, how to run and install this.
Yes, so that's end of a demonstration part. Let me go back briefly to
And we have lots of questions.
That's
Whenever
great.
you
Yeah.
are ready, I will put those on the screen for you.
Then let's do
just 1
that.
second.
In the meantime, we put on the page for with a slide. Yeah, but that is self-explanatory. Yeah, let's start. So first, okay. So if you want to install it, here's the instructions. We recommend to create a proper environment because it depends on some packages and standard practice basically. And there's documentation. 2.0 is not released yet, but there's a very stable release candidate that we recommend you install because it's got much improved performance over 1.2. All right, questions. So
Blue Tyson says, how far have you scaled this in practice?
Okay, and scaling means in terms of observations and in terms of features, right? So, I mean, the performance of this depends mostly on the performance of on the number of variables you have. In practice, we have applied this approach with with problems that had over 6,000 or over 7,000 variables. Yeah, for example, in manufacturing, in very complex set point optimizations. But what usually happens is that we narrow it down to maybe 20 to 50 candidate variables, and then apply this explanation approach, simply because if you have more variables, the chances of having lots of irrelevant variables is very high. But it's absolutely practically usable with, I would say, 50 to 100 variables. It depends a bit on your choice of model. Yes, great. Narendra, I see your question here. There is a paper. You can find the link on the GitHub repo. Yeah, we point to it.
Yes, we will send it also on Discord.
Yeah. That's a very good question, Narendra. Right now, we weren't planning to contribute. Yeah. Now, I mean, what we have done so far is that we stay on top of new releases of SHAP, and we sort of compensate for changes in the library internally. So we have a wrapper class around it. What we are considering is to implement our own vanilla SHAP explainer for that reason, right? So that using the SHAP library becomes optional. Yep, we will provide Mateusz, you will provide a gist, right, of the yes. Notebook, and we'll share it afterwards. Yeah. Very good. Okay. Okay. Yeah, Matthias, same. We will share a gist of the notebook, and if you head over to GitHub and the FACET documentation, yeah, especially using that link here, using the 2.0 documentation, you will also find additional example notebooks to look at that explain the approach in more depth.